Let's have a look at what we achieved last time. I hope this will display. It does. So we met the system which can this time properly evaluate possible moves for each side and execute on these moves, including promotions. Though so far no logic. I'm just simply using the first move that's spit out by the system until there are no moves left to do. So in theory, this was a fully functional checkers game, just a very boring, very stupid one. But that part worked. Now today I want to try and create the min-max tree. When I say try, I mean try. I'm not sure if this will actually work out decently. And we're also not going to worry about the performance. This is going to be very inefficient. So the first thing I'm going to do is limit the board size. Do we just go with 4x4? Actually, let's maybe just make 2. Less options. So very small board. We're just now stuck in an internal loop, which is probably not the best idea. That means we do have to implement the loop check anyway. Yeah, that might be good as well. Let's just... wait, did I move? No, that's fine. Alright. The tree. We would start with a board, and this board needs to be modified by applying a move. And then we make the next check. We have already the creation of a new board and we get the possible moves, so we have everything to create the new node. We could make a very simple tree structure for now. Oh, I would like to have a system that lets me check, a reliable system that lets me check if a specific position already exists within the tree. That's actually an interesting challenge later on for the calculations. I've never done a min-max where we have possible loops. It was the only time I really used the min-max algorithm before was the case where the tree had definitive leaves. There was no looping possible, which made calculations very easy. But this isn't a pure tree anymore, right? Depending on how I do it. I could just go into the same node as different nodes and just say at some point, okay, this is looped enough, we're gonna stop. No, that doesn't make sense. We're gonna have to link to the other nodes then. So I need a system to evaluate if a node exists. And to quickly find that. How do we arrange that? A simple tree is not good then. I mean, I still want to have different... I want to have some kind of structure. Let's just write that down. Probably a node for now. And that will store the state. Let's just use fields for now. Oh, right. Sorry. Yeah, state. Maybe this can get removed. So, we have a node that contains the state itself. And that should link to a set of nodes that can be reached from there. Node, yeah, honestly. For now, let's just use an empty array so we know how to populate this. I mean, one option would be, the fastest option would be if I just create a proper hash now for the state and comparisons. So proper equals, including the hash, and then create a dictionary. That way I can quickly find the matching node in the system, but that means I have to... I mean, I'm only linking to the nodes, I'm not storing them twice. It's just a separate lookup for these nodes. I think that's maybe the best option I have. Maybe instead of doing it like this, just assume it's getting filled by that. It's just a pure container, and we have a class for, let's call it min-max. And we're gonna start with a simple state, the initial board. I'm gonna save that. And we should be... Actually, no, let's not put that in the method. Let's make that inside the constructor. And this will also store dictionary. And we're not focusing on performance today, just not working. Are we going to focus on the node? No, we're going to focus on the state. Makes more sense. State and then node. And we're gonna assume that each state is unique, which it is, so we don't have to store several nodes, which wouldn't be possible then. I'm gonna do it like this. Yeah, that should be fine. Let's new dictionary state nodes. Can we estimate how big this list will be? How many possible states we're gonna have? I don't think I can properly estimate that. I mean, sure, there should be ways to limit that, but I'm not sure how. Checker seems simple, but there are so many different things that can happen. We'll just leave it as is. Or maybe let's... Nah. I'm worried I'm making assumptions now and gonna initialize it wrong. How did it... It's going to the next prime, so it's not really worth it. Let's just keep it as is. And then we gotta do... We still have to implement the hash and equals functions, but for now, let's just assume we're going to add a new node, and that's nodes add for the initial board. And that's gonna be a new node with the initial board and an empty array. No, we're not going to do it that way. Actually, I don't want to put that in a constructor at all. I'd rather have that as static method. Generate map. I can't call this tree anymore. I mean, it's supposed to look like a tree. But considering there are loops in there, it's not gonna be a tree. They're gonna be leaves, sure. One root and several leaves, but there are loops in between. How do you call that? Tree with loops in there. It's just a graph now, isn't it? Just very peculiar shaped graph. Well, let's leave it at this. Map, still with the initial state. Or initial board. And still with dictionary, we'll just copy node, nodes. Still no idea how to estimate, so we'll leave it that way. And now we're gonna have to iterate through all the different nodes, the different states, create new possible states, add them in, and if it's a new state, so I guess we're also gonna do a queue. States to process. Again, everything very inefficient, just purely getting it to work at all. Yeah, and then states to process will get and queue. It's a queue, not push. It's not a. Do I go for a stack instead? It's probably better if I go for a stack. Depth first. Should reduce the size of the structure a bit, at least of our stack then. So process, push, initial board, and then while process greater than 0. So while we have something to process, we'll go through the same steps. First, let's start. Do we have a triad? Actually, I want to be a bit efficient here. But do a contains and then an add, that's a bit wasteful. Nah, let's do a triad. That was fine. Triad. Oh, states to process. That up. Single variable state. And then we're gonna need a new node. And I don't have creation factory for that. Wait, no, I have to. I have to change the nodes after the fact, so... Well, this is annoying. That's, Did I mess up already? Do I need this? Okay, what's the end goal? I have a dictionary that contains them now, but that's only the possible states, and I can always go through there, and the point was to link them back to each other, so I have somewhere to backtrack from a leaf to where I am. To always have exact knowledge about which possible situations I can get into from each state, to know where the winning tiles are, or where the winning branches are and where not. So I should probably start with just an empty node. No. Instead, if... Well, also doesn't make sense. I could get to the state at any point. Maybe you should work this through from the point of view of nodes. Instead of going through the possible states, I'm going through the nodes directly. That makes more sense, doesn't it? So this should be node. And this will be a new node with initial board and an empty array for now. Let's process node. Yeah, that's better. And now I'm trying to populate that node with next nodes. That's my goal. So I'm changing the next nodes after it was created. That means I go through node.state. Does it get possible moves? For each move, what do I... Let's go with a list for now. This state, possible states, your list, whatever. Efficiency can be ignored for now. We can ignore validation because that's also in possible moves already. So we just apply the move. Possible states at... yeah. So we get a list of possible states that follow in that node, and we use that to create a bunch of new nodes. Node or next nodes will be possible states. New node state. Actually, let's just drop this because not really need it. If we always initialize it with just the empty array, that means we have next nodes in there. No, I still need to get the next nodes, but then I need to... No, I need to do this in one go. Again, I have to store the nodes directly, because now I have to actually... Next nodes... First I have to apply this, yes. Possible state. Now we have to actually use the dictionary again to check if it's already in there. That's what we also have to... That in there... Initial note. Initial note. Initial note. There we go. Initial note. Will get added to the stack and to the nodes. Actually, initial board is fine, yeah. Like so. We get that in the dictionary. And in the stack. Yeah, that's good. We apply the possible move, get the next state. Now we have to check if we have that already. So we go for the nodes. No, we go for nodes, not node, try get value. Based on possible state. Oh. No. Note. Next note. Alright. Nullable. If we do find a note, then next nodes. Next note. Directly. Actually, we can skip that and just make this inverted. So if we didn't find a match, if this is a new state we've never seen before, we just create the next node ourselves. So it's gonna be a new node with possible state. So we're gonna add that to the list of next nodes. Then we also have to nodes to process. Push that in there. Next node. And we have to add it to the nodes overall. Next node. Alright, so we'll stay at next node, like that. So whenever we create a new node, we add it to the, like a truly new node. We add it to the stack so we can process that further. And we also add it to the dictionary entire map of everything. If it's a node we already have, if it was already stored, we just add the one we have referenced to, basically loop back to further up the tree. That should do the trick, and then afterwards we can simply store that as an array. Why do I store that as an array? I do not know. Because they're simpler. Possibly take less space. I mean, of course, memory for building is one thing, but bah, it'll work out. That's how we fill that up. It should all work out. And then in theory, we should be completely done after that. Now the question is, do we... I'm not sure what I want to store in here. Like how I want to store the data. The dictionary is very valuable. So it's not just the initial node. I want to keep the initial node, I think. Maybe. Do I want to have the node actually? Do I still need it? How would I use this information? Technically I have my tree, if you want to call that a tree. Guess we can start calculating. Wait, I should... This tree is actually the wrong way around, isn't it? Like I can find my node from the top. This is just the full game tree of my possible choices, but it's not helping me calculating everything. I need to have a reference back to my parents from a state. At least I know that loops are only upwards. No, they can also happen downwards on a different branch. Kind of. And that can only move forwards. Once I have promoted pieces, they can go backwards, but that's a different state. I can go there in different ways. But it should not be possible for me to go downwards by following the parent. But then I have different parents. Let's change this up a bit. Let's turn this into a list to avoid a bit of redundancy. Like that. Actually, do I? I don't need to store that separately. I can just go for next node directly. Save me that trouble. And when I create a node... No, I shouldn't do that when I create the node. I should... okay, I'm still worried about the loops. That's gonna be an issue. Okay, how do I actually calculate this now? That's probably the interesting part. What I was going for initially was just... Yeah, let's just draw it out. Maybe that helps, drawing it. Where's... Nope, that's the wrong one. Screen share. There we go. Alright, so initially what I would go for in a min-max, I would go for the different nodes and see where they take me. And then once I reach my limit, once I hit the leaves, I know if I either won or lost. Could give this 1, maybe I won. This one I lost, won, lost, 1, lost, 1. So it's a bit of uneven chances. And then going further up the tree, this would be 1, this would be 1. This is a 0, the 0. This is a 0.5, because I'm just taking the average of the child leaves. This would be the 0, and then this would be 0.25. This would be 0.5 again. 1, 1. This would be just a 1. 0, 1, that's 0.5, 0.5, 1.5, that's 0.75. And if I want to be a smart ass, then I can calculate at the top. What's that? 6,125? Oh, wait. Yes? No, 125, that's correct. 6,125. No, it's not correct. I think of what are 625. 125 added, not 6,125, just 125 on 5, and then 125 again. Okay, so my chances of winning would be overall pretty good. A better than 50% chance of winning if I start, I guess, if we look at it that way. And this is how I would calculate what I do. Like, my first choice should be into this branch. That gives me the best overall chances. Because this branch I'm guaranteed to win, this branch 50-50. And on the other side, well, I have only 50-50 to start with. Then 0% if I go in that branch, guarantee in that branch, and only 25 in that branch. I did make a wrong calculation, that's not 2.5. Went wrong there. So that's 125 by 3. Ooh. 40... 42, roughly. Should be about right. 0.42 times 3. 26, yeah, about. So the total chances. 565 about. Okay, so the overall chances on this branch, less than 50, pretty good chances on this branch. That's how I would calculate the min-max and create the best possible plan for giving me the highest chance to win. Now that's what I would do if I had a clear path from top to bottom. Just one direction every single edge. But our graph has loops where they can suddenly be interconnected. Like these could be the same, or this could be referring to this one as well. And then it wouldn't be a leaf anymore. That could be, this one could go back to that, or maybe this one can go back to that. And this one might go also back to that. And these two might be connected. Like all these weird connections in between. So I would still start at the leaves, because they stay. We still have leaves. We have still cases where the board cannot change anymore. We do not have any open moves left. And I still need to go back from those definitive cases. Should I maybe ignore the loops? No, I shouldn't then. In a real play, those loops are still useful. Like if I'm stuck, for example, down here in this branch, I can use this loop to go back up and maybe force myself into this other branch where I'm guaranteed to win. So this loop is still very much useful. In a way, they extend the length of the game, giving the enemy more chances to make mistakes. Or a chance for me generally to go back and fix one of my mistakes. So we assume the computer doesn't make mistakes, but anyway, those loops are important for the calculation, but how do you calculate that? Because in theory, you could go through this branch any number of times. But the overall state doesn't change, we're still at this or this, so... Do I actually want this number to change now? Well, the direction would be this way, and that's how I would go through the tree usually, would backwards. But that means if I go up and up and up, then I have to suddenly decide, do I go further up here, or do I take this branch and go backwards through here? If I do that, I would need to update the points in here. Because I always go back up and then calculate the value. And actually I go down the tree and calculate the tree from the node top. Go through the children recursively for each child. Go through both sides. Calculate that value. Go through that value. Go through that value. This one is a fixed value, then this one is that same value in theory, but this is a chart then. To calculate the chance of this and this, and I can calculate the chance of that. It doesn't make too much sense. So in terms of points, it is a valuable thing. It should affect the chance for a branch. But at the same time, it's not something that should affect my chances. It's... oh god. I completely blocked out the loops, so I have no idea how I would implement this with a min-max. Like, what is the best way to calculate the points now? I could just try to ignore them. If I go recursively down from the root, I can just keep a hash map or something of all the visited states, or all the nodes I have already seen, and then simply ignore the child nodes that are just looping back. So if I go down here and see it has two children, technically, this one and this one, I know I've already visited the upper one here, Can ignore this connection and just focus on the child, in theory. But how much does it change the value? How do I determine the value? This one doesn't give me anything. So that would be an example of a loop that's not benefiting me in any way. It's also not hurting me. It doesn't matter if it's there or not. This loop here is an example of where it absolutely matters. Because I can switch branches up here. This would also matter, this connection here. Going from this node, which has a guaranteed win, to this node would be pretty dumb. Wait. If it's only my decisions, then I shouldn't take the average, which is an interesting metric, sure, but it's not what I should focus my decision making on. I mean, the whole min-max is just for the computer to make decisions. So maybe I should change the value based on that? No, that's not. No, the average is still good. But in those cases where I loop back, I should maybe try to combine them. Like in this case, if I go back, I already have the value of that node, so I can treat this thing as having the value of that node. So this would be split between a loss, a win, and a 75% chance. But then it would retroactively change the value again. I know, I go down here, it has 0 and 1. Then I go up to this node and try to calculate the average, but that would be this node here, this node, and that node. And then I would get stuck in a loop again for the recursive action. Why? The loops are killing me. I could make this a 2-pass, maybe? I don't want to do that, but I could make this a 2-path where I first ignore the loops, make all the calculations, and then make a second step through where I include the loops and recalculate based on the original scores, but now with the loops in place. So I would have data for this node, for example, from the initial pass, and I could use that as the score for this child, so to speak, if I treat this as a child. I mean, it is a child of this node. And that would then update this node to 75 by 3.88. So this thing would go from just 7.5 to 8.8, which reflects the whole thing. But then this node would also update the value on the same node. Going from... This would now be 1 and a 7.5. So we go for an 8.75. This would be a 1 and 8.75, so we go to 6, 9, 4, 7, 5, maybe? I can't math. I once was able to math, and since then I just got worse and worse. And now I can't do math anymore. It is about 9 or something. Wait, what am I doing here? There we go. 9, 4. That could be interesting. I think technically I should make another pass after that. With all the updated values, updated scores in the second pass, where I include the different nodes for the loops, I would then need to recalculate again. And again and again and again and slowly refine the actual score. And that seems like it's a roundabout way for a very simple direct solution. It could also be that it suddenly starts to flip-flop between two values and I'm not approaching anything. Don't like that. I don't like that. How do we calculate the scores? I mean, in a way, you can treat this as this branch on the left is guaranteed to win. This one on the right has a 50-50 chance of winning. But the one on the right offers you the chance to go back and try to redo your decision here, which means this whole tree is also sort of guaranteed win, but only because you can skip it, which means you shouldn't go down this branch, which you wouldn't because there's a guarantee on the left. So this should not be equal to 1, it should be less than 1. But it should probably reflect that we can correct the mistake. Maybe I should leave out the loops at all. And now the screenshot just stopped. Why? What's happening again? Okay, but I'm done with my tree anyway. Let's just try to ignore the loops. How about that? Let's just make a simple calculation first without involving the loops. Okay, and then let's do it like this. Public. Do I actually do that in here? Let's make that outside. Let's keep this thing done. Public and actually let's keep float score. Don't need to make that too big, so just keep it at a float. Not that it changes much considering how big the other types are. Score starts with a 0. Let's go for -1. To mark this as nothing initialized yet. It doesn't have a score of 0, which would be just loss. It has nothing in there yet. No, wait, I have to actually do 2 scores. One score for player 1, the other score for player 2, because we have 2 players that could technically play and win. And of course they will have pretty much opposite scores. No, they will have exactly opposite scores. I don't need to store both, I just need to know one. I can just invert it. 1 minus score will be the other player's score. Okay, we're fine. We just have to decide which player's score that is. Player 1, probably. Makes most sense. How do we do this now? We do have a stack already, which we probably can reuse, but now we... No, we still want to do depth first, right? Makes more sense. We have to go depth first, we have to go down to the leaves. We have to go down there as fast as possible, so yeah, we're gonna reuse the nodes to process. But I'm also gonna need a hash set. Okay, but now we have an idea. Processed nodes. Processed nodes. Do I just store the nodes? Let's use not the nodes, let's use the processed nodes by state. So I don't have to implement the whole hashing and equals check for the nodes as well. So it will be a new hash set, and we can initialize it with nodes dot count. Since we know that's exactly how many unique nodes we have. And by the end, we probably have filled everything. We should have filled everything. Then let's continue with nodes to process. I'm gonna push the initial node once more. Also process nodes by state. Add process node by state. Dot state. Dot initial node. Sorry, initial node. Board, yeah, that works fine too. And again, while nodes to process, count greater 0, 0. Okay, this time it worked. Nodes to process. Count. No, this is gonna be... No, this is not right. Let's forget this part. We can keep that one. That's fine, but... we're not gonna reuse the stack. We're gonna make this proper recursion. Because I... Is it offering? Yeah, fine. I can't be bothered to implement the recursion inside the stack, and this is just gonna make it easier. Public void, calculate score, and hash that state, processed states. Right, and then we go through the child nodes, next nodes. Actually, let's call them that. Makes more sense. Float, what's on a float? Sum 0. Yes, autocomplete, that's actually what I want to do. And then sum plus equals calculate score note. Note dot like that, and then process states. And some divided equals by child nodes dot count. And if child nodes count is less than 1, return 0. Should not harm us, right? If I don't have any children. Oh wait, now I have to calculate if I'm actually winning or losing. Okay, this is child nodes count less than 0. Then we're gonna go to state. State dot player 2's turn. Okay, so we have no more moves left, but it's player 2's turn, then we won, because that means player 2 has no more turns. If it's false, that means it's our turn, but there are no more moves and we lose. Okay, so in case of a leave, it's a clear win or lose. Otherwise, we have to actually calculate the sum of all the different scores. Which also means no division by 0 anymore. Convenient. And we have to exclude loops. That actually means we have to do this. We have to actually use this process states dot add node dot state. Only if we successfully added this as a new state, because it wasn't in there, will we include the score. If we added it with a false, that means the state was already stored in the hash set and we can ignore this because it's a loop. Let's still remove this. Nah, that looks bad. Let's keep it like this. And then don't actually need to do this, right? Return that. And that is in there, correct? And then initial node calculate score. Process nodes by states. And wait, no, I have to. No. Yeah. Okay, looks a bit weird, but forgot we have to store our score as well. So we can look that up later. We want to actually remember the score. So -1, negative value, we haven't initialized yet, we haven't calculated it, but everything above 0 means, or including 0 means we have calculated, and that's our chance to win as player 1. In theory. So this should be the calculated score for player 1 to win at all. So then the question, do we return the dictionary or the initial node or both? Probably easiest if I just go for dictionary. In which case I don't need to create it. Yeah, let's just... Don't need to store that in min-max. Just return it as is. The node contains everything we need. Give it a try, maybe. Just see what happens. And render, rekey, and then let's calculate quickly. Max.generate map for new board. Let's see if it crashes or just breaks everything because it's too big. Well, it's calculating. It is calculating. You can't see the diagnostic right now. Interesting. But the program's running, and it's currently at 11 megabytes. Oh. Whoops. Yeah, it's waiting for me. Okay, key pressed, and we had... Ooh. Ooh. I hope the stream might crash. Sorry in advance. It doesn't like that. Oh, I'm breaking. Okay, let the computer calm down for a moment. It jumped up to 1.5 gigabyte memory and then stopped counting, which is not a good sign. I hope the stream is fine. So your stats are looking okay. Seem to be live. Okay, I guess that's still live. Maybe we're just gonna step through it and maybe on a smaller map. Let's go for 3x3. 1 token each. I stopped again at 1.5 gigabyte. Might have included an eternal loop. Oh, wait. Oh, of course. I messed up. I didn't implement the state yet. Didn't check for doubles because this is not implemented yet. Whoop. It cannot distinguish between two states. If I generate the same state twice, with exactly same values, it will treat them as different states. It's alright, get HashCode for now. Bit array. Can I trust the HashCode for bit arrays? You know what? We're gonna find out. Let's strictly go to source.net. Just gonna look up quickly in the source code for bit arrays. Bit array. Actually, can I window capture properties? I do this. Okay, that didn't quite work out. Transform. Okay, this is what I'm currently looking at. Source.net. Very useful little tool. Can look up basically the source code for .NET or the standard classes. If you're not sure about something, you can look that up. So I'm currently looking for get HashCode. Maybe I'm blind. Let's just search for it. Hash. Doesn't find hash. So it doesn't have a specific hash implementation. I think we can treat that as don't trust the hash. It's probably just using the default hash code then, unless I overlooked it severely, but I guess we're gonna have to do this the classic way. Is there any fast? Nope. Okay, let's go for hashcode. Let's make a new hashcode, and we're gonna return hashcode. Then hashcode dot add. Yeah, that will work. Occupied for each pool being occupied. Add. Good. Now this is not going to be efficient. Once more, I mean, nothing in here is. Color. There will be faster ways to do this. I mean, for the efficiency, this whole record will be changed anyway at some point. Just to keep the size down and to make it easier to copy and a lot of other stuff. Noted, and then what do I have? Stop meta width and heights. Okay. Dot add metadata width. I'm wondering if I need to include width and height, since they won't actually change. But well, let's keep them there. By the way, hashcode, very useful class. If it's less data, you can also make that in a single call, but I had to do that in an object. That's useful though. Equals other. If other is null. Return false. Return other dot occupied. Can I do sequence equal? No. Okay, let's do it this way. Occupied if occupied dot count unequal other occupied dot count return false. Let's do that a couple of times for color and promoted. Color promoted and promoted, so at least we know they are equal. Let's also make a shortcut for just the basics. Let's call metadata width and height. Okay. If metadata not equal other metadata or width not equals dot width or height unequal other dot height. Return false. And if that all didn't quite work out, then we're actually bothering with checking the bits themselves. See, I want to make my own bit array for the optimization. Then I can make also some very fast comparison. Instead of bit by bit, I can take entire arrays full of bytes and compare those. Maybe I should stack them together. Make them a cluster of 4 or 8 bytes. Basically compare ins and logs. Take advantage of the CPU. But putting that together might take more than it's worth. No, wait, there's byte arrays I have built on logic, right? Can make system calls for that? I think there was some memcheck or comp. Some system calls I can do for comparing pure byte arrays. So I should be able to make use of that for comparing for later. Have to keep that in mind. Occupied 0, I less than occupied.count plus I. We know that all 3 byte arrays are the same length, so we're not gonna bother making this 3 times. And we're just gonna compare if occupied I not equals other dot occupied I, or also this check, instead of having these ors here, maybe a single or to reduce it to single operation, less branching, but color, promoted and promoted, and false, and then return true. Now we should have a proper equals. Let's try that again with our small board. And we jumped immediately down here, which is good. Is the result actually any good? Oh wait, wrong breakpoint. My mistake. Let's see where we go. That was fast. Okay, that's good. We got a couple of different possible states. Let's make this a bit different. Debug a display. Just use score. Score. Chart nodes. Out. Wait, I'm not sure if I can do that. Result count. Maybe I can't do that in here. Okay. Let's just use the count, the score. Let's try this again and try a map. Well, that is disappointing. Everything is 0. I mean, it did generate something. We just meh. Guess we have to go in here and debug and see if it made any significant errors. Let's just, yeah, let's just put that out. Okay, so generating all that, sure, works. So we'll create a new node here, which makes we should have. We have a 3x3 grid, so this very first move by player 1 has 2 possible moves, which creates 2 distinct new states, which is what's happening right now. Okay, that was that. That means we have 2 new nodes to process. This time for player 2, which only has 1 option. Sorry, was distracted by something outside. So we have only 1 option here. Player 2. which is depending on what the player 1 chose. That was that. Okay, player 2 now has only one option left. That's right. And based on that state, this should be player 2 now, with no options left. Where was their possible move? Wait. Let's look at state. Which are we? We are at... We have node. And the current state for node... Okay, plus 2 turn is true. Yeah. Oh, right. We have only one token, so the top space is free. No, then everything is correct. And it's getting promoted. Now player 1 is in charge. They have a promoted piece. So they have 2 options once more. Which will be 2 new states, because we didn't have that situation with promotions yet. And then player 1's turn. They too are promoted now, and they only have 1 option left again. Now player 1's turn. They will have now 2 options, either going up or down. Actually, you know what? Let's... I have an idea. To make this a bit more interesting, let's say state render prepare, state render render. Yeah, let's just do that near node.state, so we can actually see something. Read just gonna intercept, and we're just gonna look at the... So this is the state it looks at now. Next state. Okay, this is when it basically jumped back to an earlier state and checked the alternatives. Why are we stuck in this loop? Let's quickly make a breakpoint here. Advance. The loop is not hitting. Oh wait, I didn't set a breakpoint down here. Oops. Yeah, we never are running out of options then. That makes sense. Let's try that again. Okay, now we had all options through. So we had 19 different options. Okay, so that part seems to work. Okay. Then why are they generating the data wrong? Let's make a breakpoint down here, and guess make a breakpoint down here when they return the leaf values. I feel like am I making a mistake here? Okay, we'll see. Well, that was quick. Didn't take my breakpoint, so what is going on? Let's reset the program. Two channels, which is correct. Oh, right. Because I'm hitting leaves that are technically leaves. Because they represent a state that can only return to an earlier state. This is basically part of a loop. This is where the loop starts at a leaf. Or what's otherwise a leaf. So this check has to be actually done up here as well. Yeah. How do I make this? Forget efficiency. Let's just make this simple for now. List note valid non-loop child nodes, and this is gonna be new list, which we're just gonna instantiate with child nodes count. Definitely gonna be a bit larger than necessary, but we don't have to make a second. What's the term? Allocation. Allocation, that's the term I was looking for. Non-child loops. Non-child loops. Can I make this? Ah, let's just make this copy. If non-child blah 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 dot add. Note, and for each non-loop child nodes, and we can delete this, and we can also delete this. We can make this in other ways too. Instead of storing that, just going through the enumeration and then just have something like a simple boolean set if there's any doesn't matter. We could just check the count. You know what? Let's be fancy. Let's be fancy. Fancy, it says. Count equals states.count. Yes. Will count. We're doing all of that. We have the sum, that's correct. If browser states count equals initial count, let's leave it up here as well. Just in case there's a true leaf without any loops involved. But we still have to be careful down here, and otherwise we have to make diff here. So, at the cost of an extra integer, we know exactly what happened in here without having to store the result. So we can calculate these scores recursively, and we still know if we were part of a loop, in which case we can skip a lot of the stuff. That should be it. That did calculate the score, which is interesting. Yeah, the loops again make things a bit harder. Let's look at this. At least there are some nodes that are guaranteed to win, which cool. Very unlikely to win. So in my case, player 2 has an advantage. Okay, the calculations are still wrong. But it's not like any player can win. This is a no-win scenario on this board. Neither player can actually win, because there's always a move you can make, but the move you can make, if you basically have rarely the chance to actually do something different, and the only choices are always giving the other player only one choice to move, which also is just, you have never the option to jump over another player. Let's put it that way. Let's make this a bit bigger. Let's see what this looks like. Still pretty fast. That's good. Different score now. Actually, let's return. Let's make the breakpoint on here. So we have 85 possible moves. But in this case we have some options. To win. But it doesn't look like it. So the calculation is probably still wrong. I might need to add the whole thing to the visualizer. But that's for another time. I can't be bothered to figure out what's going wrong right now. Technically the program does something without breaking, which is cool. It calculates the score, which doesn't seem to be correct. But it's doing something. We'll have to check if the tree is actually correct, but I think it is. That might be the issue, that the tree is generated in the wrong way, which would explain why the scores are so off. Could also be that both are wrong. But, well, that's for next time. I will play Sunday afternoon, or evening, or morning. Or Monday morning? Whatever. Bye.